At this exact moment, 8 minutes is enough to change the map of our sky. A camera in Chile opens, closes, opens again. Tiny points appear, then drift, then multiply before anyone can catch a breath. And somewhere inside that rush, a new machine finds what the world did not know was there. If you live for the second mystery turns into proof, subscribe right now. Stay close if you want real space stories told with wonder, not nonsense. Because this one starts fast, and it does not slow down. For years, the Vera Rubin Observatory sounded almost too big to feel real. People spoke about it like a giant promise sitting on a mountain and waiting for its first true moment. A telescope would scan the sky again and again, not once, not twice, but for 10 straight years. It would build a moving record of the universe, and many people wondered if any machine could really do that. The idea alone was enough to make astronomers excited. Rubin was not built just to take beautiful images that end up on posters or computer screens. It was built to notice change, which is much harder, because change can be faint, fast, and easy to miss. A star can brighten, an asteroid can slide across the dark, and a whole discovery can vanish if nobody is looking at the right second. That is why the first public reveal mattered so much. The world was not just waiting for a nice picture. The world was waiting to see whether this observatory would arrive as a showpiece or as a real discovery engine. On June 23, 2025, that answer came fast. The observatory is named after Vera Rubin, the astronomer whose work helped prove that most matter in galaxies is hidden. She studied how galaxies spin and found that their outer parts move too fast for visible matter alone to explain. That missing pull was blamed on dark matter, a simple name for something we still cannot see directly. In other words, Vera Rubin helped show that the universe is stranger than it looks. So the name on this building is not decoration. It carries a message. The sky is full of hidden things, and old ideas can break when better tools arrive. That message becomes even stronger when the machine carrying her name starts exposing what we have missed. Rubin Observatory stands on Cerro Pachón in Chile, high above a dry landscape with dark, clear skies. Places like that are gold for astronomy because clouds, moisture, and bright city lights ruin clean views of space. After decades of planning, building, testing, and waiting, the observatory was finally ready to show what it could do. When the first imagery dropped, people did not just see a telescope turning on. They saw a new era opening. At the heart of the system is an 8.4-meter telescope and the largest digital camera ever built for astronomy. That camera is called the LSST Camera, and it holds 3,200 megapixels. It is about the size of a small car and weighs nearly 6,200 pounds, or about 2,800 kilograms. Each shot can cover an area of sky as wide as about 45 full moons. That single number is easy to hear and easy to ignore, but it explains why this observatory is different. Many telescopes can look far away, but they see only a small patch at one time, almost like peeking through a keyhole. Rubin can watch a huge part of the sky at once, then come back again and ask what changed. That is the real power. It is not only depth, it is not only detail, it is the mix of width, speed, and repetition, all working together night after night. Scientists expected Rubin to become useful over time. They knew it would matter once its main survey settled into a steady rhythm. They expected the first public images to be impressive, maybe even beautiful enough to dominate science news for a day. What many did not expect was how quickly the observatory would already start proving itself with hard numbers. In just over 10 hours of test observations, Rubin captured millions of galaxies, stars in the Milky Way, and thousands of asteroids. That was not after years of work. That was not after a long completed survey. That was almost right out of the gate. And that is when the internet reaction made sense. People were not only staring at deep space beauty, they were realizing that this new machine had already started changing the count of real objects in our sky. The story was no longer, wait until this becomes useful. It was, it is useful now. One of the first things the team showed was a huge image of the cosmos field. The public view began close, then kept pulling back until the scene became crowded with light. The final image was made from more than 1,100 separate exposures. Inside it were about 10 million galaxies. 10 million galaxies already sounds hard to believe, but the bigger shock comes after that. Those 10 million galaxies represent only about 0.05% of the roughly 20 billion galaxies Rubin is expected to record over 10 years. This means the so-called first look was less like a full reveal and more like the smallest sip from an ocean. That matters because scale changes feeling. A telescope that sees 10 million galaxies sounds powerful. A telescope for which 10 million galaxies count as a tiny sample sounds almost unreal. It forces you to stop thinking in pictures and start thinking in floods. Did you expect the opening move from a new observatory to be a scene so huge that 10 million galaxies count as almost nothing? If that number hits harder the second time you hear it, tap like and tell me what your brain does with it. And subscribe now, because the next part is where the story stops being beautiful and starts being urgent. Another first image focused on the Trifid and Lagoon nebulae, giant clouds of gas and dust where stars are born. That view used 678 separate images taken in a little over 7 hours. These glowing regions sit thousands of light years away, which means Rubin caught light that began moving toward Earth long before any of us existed. By stacking so many images, the observatory pulled out faint shapes that would stay weak in smaller views. This was important, but still expected. Astronomers knew Rubin should be good at producing wide, rich images of deep space. That was part of the plan from the beginning. Then the moving objects arrived, and the mood changed. Because beautiful images make people stare. Moving discoveries make people rethink what the sky even is. Most of us grow up thinking of space as distant and quiet, almost frozen. Rubin's early data said the exact opposite. In about 10.5 hours of open shutter time, across parts of 7 nights in April and May 2025, Rubin found 2,104 never-before-seen asteroids. Not in a full year. Not in some future survey after endless upgrades. In a few nights of early observing, while many people were still learning how to say the observatory's name. And the details made it even more shocking. Among those new finds were 7 near-Earth asteroids. There were also 2015 main belt asteroids, 11 Jupiter Trojans, and 9 trans-Neptunian objects far beyond Neptune. Rubin also picked up around 1,800 already known objects in the same dataset. This is where the gap between expectation and reality becomes hard to ignore. Scientists expected Rubin to be good at asteroid hunting. What they found was a system that immediately looked like the future of asteroid hunting. It was not a slow warm-up. It was a sprint. To understand why that hit so hard, compare it with the wider world. All other observatories on the ground and in space together usually discover around 20,000 asteroids in a whole year. Rubin alone found more than 2,100 new ones in only 7 early nights. That is the kind of pace that makes old discovery rates suddenly feel small. And remember, this happened in a limited early observing run. Rubin was not yet doing its full 10-year survey at maximum routine power. It was showing what it could do in test conditions. That is why people did not treat the result like a fun preview. They treated it like a warning shot. The 7 near-Earth objects matter for a reason that goes beyond excitement. An object near Earth does not mean a collision is coming. It only means the object's path comes close to Earth's orbit, which is enough to make scientists pay attention. The more of these objects we find early, the better our map of possible danger becomes. That brings us to one of the most human parts of this whole story. Space is not only about wonder, it is also about safety. If a rock large enough to damage a region is out there and we have not found it yet, that is not just an astronomy problem. Researchers say we have already found most near-Earth objects bigger than 1 kilometer. That sounds calming at first, but the smaller class tells a less comforting story. Scientists say we have found only a little more than 40% of near-Earth objects larger than 140 meters. A 140-meter object is not the kind of thing that ends all life on Earth, but it is still big enough to do terrible damage. It could destroy a city, hit the ocean, create powerful shock waves, or start a disaster over a wide area. So every jump in our ability to spot these objects early matters in a very practical way. Rubin is expected to discover a few million unknown asteroids in its first 1 to 2 years. That may include around 100,000 near-Earth objects that are still missing from our catalogs. Those numbers are not just big, they suggest that our current map of nearby space is still deeply unfinished. Did you know we may still be missing tens of thousands of nearby objects large enough to matter on Earth? Tell me in the comments whether that feels exciting or unsettling, and hit subscribe if you want to follow every new twist, because this is where a sky survey turns into something that touches life down here. Then there are the Jupiter Trojans. These are asteroids that travel around the Sun near Jupiter's path and gather around stable balance points. Think of them like groups of rocks riding in space traffic pockets, held in special places by gravity. Rubin found 11 new ones in that same early burst. Farther out, it found 9 trans-Neptunian objects. These icy bodies live beyond Neptune in the cold, dark outer solar system. They are dim, distant, and hard to spot, which is exactly why new finds out there matter so much. Each one is like a leftover piece from the solar system's early building days. Those outer objects matter for another reason too. For years, some astronomers have wondered whether a larger, unseen planet might be hiding far beyond Neptune. People call that idea Planet 9. Nobody has proved it exists, but Rubin is one of the best tools ever built to test whether such a hidden world leaves tracks in the motions of smaller, distant bodies. This does not mean Rubin has found Planet 9. It has not. But it means the observatory is finally strong enough to search for clues in a serious way across huge stretches of sky. That alone is enough to keep many eyes locked on every new Rubin update. And here is another detail that made the asteroid result feel even bigger. Those first moving object discoveries came from a highlighted region around the Virgo cluster, near an area called M49. The patch was only about 14 square degrees, which is tiny compared with the total sky Rubin can work through. So the number 2104 did not come from a full sky sweep. It came from a small taste. That is why the early release felt less like an opening ceremony and more like a leak from the future. If a small patch can hide that much motion, what happens when Rubin repeats this process across the sky night after night? How many unseen objects are waiting in regions nobody watches often enough? And how many of them matter right now? This is the moment when the story stops living in the past, because Rubin is not only about what it found in those first nights, it is about what it is built to keep finding, again and again, with a rhythm no older survey could match. The mystery is no longer locked in a first reveal. It is alive in the schedule itself. Rubin's main mission is called the Legacy Survey of Space and Time. The name sounds formal, but the idea is simple. Watch huge parts of the sky over and over for 10 years, and every difference becomes a clue. A light that was not there before matters. A rock that shifts position matters. A star that flickers the wrong way matters. That repeating look is what changes everything. A normal image can tell you what exists. A long sequence of images can tell you what changes, what moves, and what behaves strangely. That is how a still universe becomes a story in progress. Rubin is expected to gather about 1,000 images per night during its survey. It will generate about 20 terabytes of data every night. That is an amount too huge for a person to sort through by hand, so the observatory depends on fast software as much as on mirrors and glass. Without smart systems, the sky would bury us in its own information. Over 10 years, Rubin's processing is expected to produce around 500 petabytes of data. Its catalog database alone is expected to reach about 15 petabytes. The final dataset should contain billions of objects and trillions of measurements. That means Rubin is not only building pictures, it is building one of the richest measuring tools astronomy has ever had, and that creates a new kind of challenge. The observatory has to notice what changed fast enough for the rest of the world to react. It is not enough to store the data and admire it later. If a dangerous object or a rare cosmic event appears, scientists need alerts while the event is still happening. So the discovery engine is not just the camera, it is the whole chain. The camera catches the light, the software compares old and new images, and the system decides what may be moving or changing. Then those alerts go out so other telescopes and research teams can look too. That is one reason the asteroid result impressed experts so much. The points of light did not simply show up on a screen. They had to be linked into real tracks, given likely paths, and passed on to the Minor Planet Center for confirmation. Rubin was proving that its brain worked, not just its eye. Have you ever seen a new machine arrive already acting like it belongs to the future? If that is what this feels like to you, leave a like, write "future" in the comments, and subscribe before the next alert lands. Because Rubin is not warming up anymore, it is teaching the rest of astronomy how fast the sky can now be watched. Now comes a twist many people missed during the first wave of excitement. Rubin's early work was not only good for press images and social media shock, it also helped produce the first peer-reviewed science paper based on data from the LSST Camera. That happened before the full survey even got going. The object at the center of that paper was asteroid 2025 MN45. This rock lives in the main asteroid belt between Mars and Jupiter. It measures about 710 meters across, or about 0.44 miles. That alone makes it large enough to get attention. But size was only half the story. What really made scientists stare was its spin. Asteroid 2025 MN45 completes one full rotation every 1.88 minutes. That made it the fastest spinning asteroid larger than 500 meters ever found. Try to picture that with everyday logic. A body wider than many city blocks is turning around once in less than 2 minutes. If that happened with a loose pile of stones on Earth, you would expect the whole thing to fly apart. Yet this asteroid keeps holding together. That matters because spin can reveal structure. For years, many astronomers have described larger asteroids as rubble piles, meaning collections of broken rock held together mostly by gravity. That idea still works for many objects, but a big asteroid spinning this fast hints that some of them may be stronger inside than the simple old picture allows. Again, look at the pattern. Scientists expected Rubin to become useful later. What they actually found was a system already reaching rare and difficult targets during early commissioning. And the gap matters because it tells us Rubin may expose classes of objects we have been undersampling for years. That one asteroid also shows something deeper. Rubin is not only good at finding more things, it is good at finding different things, strange edge case objects that test our basic ideas. Sometimes science moves forward not when a tool repeats what we know, but when it catches the object that should not behave that way. The study of 2025 MN45 used data collected over about 10 hours across 7 nights in April and May 2025. So even this result was pulled from the same young stream of observations that fed the first public excitement. The early nights were already full of objects that could force better questions. Rubin was not just counting rocks, it was finding the weird ones. That is what makes this observatory feel alive. A normal telescope can produce a famous image. Rubin can produce an image, an alert, a catalog update, a swarm of new objects, and a puzzle all at once. It does not enter science quietly. It arrives making demands. And some of those demands point far beyond asteroids. One of Rubin's long-term goals is to help scientists study dark matter and dark energy. Together, those two mysteries make up about 95% of the universe. That means normal matter, the stars, planets, gas, dust, and people we know, is only a tiny share of the whole story. That number should feel strange every single time you hear it. About 95% of the universe is made of things we do not properly understand. We can measure effects, build models, and test ideas, but the biggest parts of reality are still largely hidden. Rubin may help because it can measure the shapes, motions, and changes of enormous numbers of galaxies over time. This is where wide coverage becomes more than a technical trick. To study dark matter, astronomers need to see how gravity bends light and shapes the motions of galaxies. To study dark energy, they need to track how the universe expands across huge scales and long stretches of time. Rubin's power comes from doing this with volume, repetition, and patience. But the emotional pull of Rubin is not only in those giant mysteries. It is in the fact that the observatory links the farthest questions to the nearest risks. One night, it may help map the large-scale structure of the universe. Another night, it may catch a nearby object that needs urgent follow-up. That blend is rare. Most people think of space news as either deep philosophical wonder or practical danger. Rubin lives in both worlds at once. It can help us ask what the universe is made of, while also helping us spot what is flying through our own neighborhood. And the list of future possibilities is longer than most people realize. Rubin may detect supernovas, which are exploding stars. It may find more dwarf planets, more comets, more strange variables, and more rare objects passing between categories we thought were clear. It may even become one of the best tools for spotting interstellar visitors from outside our solar system. So far, only a tiny number of confirmed interstellar objects have ever been seen passing through our system. That small sample tells us almost nothing about how common such visitors really are. Rubin may change that by watching enough sky, often enough to catch more of them before they fade away. If that happens, every new object could become a message from another stellar system. Did you expect one observatory to connect asteroid safety, galaxy science, dark matter, and visitors from other stars all in the same mission? If that range surprises you, comment which part pulls you in the most, then subscribe so you do not miss the next reveal. Because Rubin is becoming less like a telescope and more like a daily source of cosmic interruptions. That phrase may sound dramatic, but look at the numbers again. Millions of galaxies in the first test run, more than 2,100 new asteroids in about 7 nights. A camera with 3,200 megapixels, about 20 terabytes of data every single night once the survey is in full motion. Those facts create a new normal. The sky is not just a place we visit with occasional expensive images. It becomes a stream. And once the stream starts, the question changes from what is out there to what changed since yesterday. That shift matters to science, but it also matters to regular people. A living map of the sky changes how we think about uncertainty. We stop pretending space is a finished chart and start treating it as an active environment with missing pieces. That mindset is healthier, more honest, and probably safer. It also reminds us that discovery is often less about one perfect answer and more about repeated attention. Rubin did not force the universe to create 2,104 new asteroids. Those objects were already there. We just finally had a tool that could notice them fast enough and wide enough to prove it. That is why the first reveal felt so personal to many viewers. It carried a quiet message that reaches beyond astronomy. Reality is always larger than our first map of it, and every time we build a better way to look, the world gets less comfortable and more interesting. You can feel that in the way people reacted online. Some focused on the images, some focused on the asteroids, some got lost in the camera size, the mountain, or the idea of 10 years of constant sky watching. But beneath all those reactions was the same feeling. We just gained a new sense. A good telescope extends sight. A great survey changes awareness. Rubin may do both. It may teach us that the universe is not only larger than we guessed, but busier, quicker, and less mapped than we wanted to believe. And this is still the beginning. The first imagery release was a preview. The early asteroid burst came before the main survey reached its long, steady rhythm. If this is what the opening chapter looks like, later chapters may feel almost impossible by today's standards. Maybe the next headline is, "A near-Earth object spotted earlier than any old system could manage." Maybe it is a distant, icy world tugging at the Planet 9 mystery. Maybe it is a rare, exploding star caught at just the right first moment. Or maybe it is something nobody is predicting because the best tools often find the surprises that bad imagination misses. That possibility may be the most exciting thing of all. Rubin is not only a machine for confirming old hopes, it is a machine for humiliating old limits. It can show us that the sky kept its secrets mostly because we were not looking in the right way. And if you care about Earth, this matters. If you care about the future, this matters. If you care about the simple human need to know where we are and what moves around us, this matters. A better map of the sky is not a luxury. It is part of growing up as a species. We still live on a small world moving through a place we do not fully understand. Most days we forget that because the ground under our feet feels stable. Rubin pulls that comfort away, but in a useful way. It reminds us that safety and wonder can come from the same act of paying attention. And maybe that is why this story spread so fast. It was not just a science update. It was a glimpse of what happens when human patience, engineering, and curiosity finally meet the right moment. A mountain, a mirror, a giant camera, and suddenly the dark starts talking back. There is also something almost funny about how quickly this happened. For years, people said Rubin would change astronomy once the long survey began. Then the public barely got its first proper look, and the observatory was already forcing new counts, new tracks, and new headlines. It was like building a dam for a giant river, opening the gate a crack and watching the whole valley realize how much water was behind it. The internet reacted because the story works on two levels at once. If you love beauty, Rubin offered impossible-looking views full of galaxies and glowing clouds. If you love hard evidence, Rubin offered a count of 2,104 new asteroids found in just a short early run. Very few discoveries land with both kinds of force. This is also why speed matters so much. A telescope that sees deeply but slowly can still miss the moment when a faint, moving object first appears. A telescope that sees widely but without enough detail can miss what the object really is. Rubin sits in the powerful middle ground where wide, deep, and repeated watching all feed each other. If you want more space mysteries that turn numbers into real stories, subscribe and turn on notifications right now. Like this video, share it with someone who still thinks the night sky is quiet, and drop your prediction below. Thanks for watching, and I will see you in the next one.